CH4 is methane. It's the simplest in a family of organic compounds called alkanes, and we'll talk more about that in the next chapter. But for right now, what's really strange for us is that CH4 is tetrahedral, all right? 4 clouds around it, they want to be far apart. And again, the same question, how do you account for those atomic orbitals at 90 degrees at best and maybe no degrees if you're an s orbital? How do you go from there to tetrahedral 109 degrees? In this particular example, we're going to use 4 atomic orbitals. We're going to use s and all 3 p's, and that's going to make 4 hybrid orbitals. Now in the BF3, we used s and 2 p's, and there was an extra p left over we didn't use. All right, but in this one, we're going to use all 4 of them, and if you have 4 orbitals with the same energy, they will naturally point in the correct positions in tetrahedral because they want to be as far apart from each other as they can. And again, it all comes down to electrons and electrons repelling each other. That's what makes them in the 109 degree angle. They want to be as far apart from each other as possible.
The valence orbitals of carbon are the 2s orbital and the 3 2p orbitals. When these atoms form methane, their orbitals are thought to hybridize to form 4 equivalent orbitals. Because each hybrid orbital for the carbon atom is composed of 1 part s orbital and 3 parts p orbital, they are called sp3 orbitals. The energies of the hybrid orbitals are the average of the original atomic orbitals.
Okay, lots of information in that, so let's think about this. Let's go to the punchline, though. If you have a molecule like carbon in methane right there, and it's in a tetrahedral environment, you will refer to that as sp3 hybrid orbitals, all right? So we would say that the carbon is sp3 hybridized. And the sp3 term, again, comes from the fact that to make this happen, we're taking 1 s orbital and 3 p orbitals, i.e. the 2s and the 3 2p's. And in the video, I like it because initially it showed the 2p's higher energy and 2s under, and that's why we fill in 2s before 2p and 2p before 3s. It's the n plus l rule once again. But anyway, if you mix those 4 orbitals together, you haven't created or destroyed any energy, and that's the first law of thermodynamics, and that's really important for chemistry and physics and all this kind of stuff. So we're not creating or destroying any energy. We're mixing these orbitals together so the s goes up and the p's come down, and you end up with 4 degenerate, which means same energy, 4 orbitals with the same energy. And the paired 2s electrons, by Hund's rule, will jump ship. You then end up with 4 individually occupied orbitals, which we call the sp3 orbitals. And again, that's because they're from 1 part s and 3 parts 3. And anytime you have a tetrahedral electron pair geometry, that's going to be due to an sp3 hybridized orbital, which is a pretty cool thing. So that's a cool video to watch. That's one of the more important videos, I'd say, of this whole class. And if you want to rewatch it, that is fantastic. But let's look now at what happens when you take the 4 sp3 orbitals and you add hydrogen.
A methane molecule forms when 4 hydrogen atoms form sigma bonds to the sp3 hybrid orbitals of the carbon atom.
Just like on the boron example we looked at earlier, that was sp2, each of the sp3 orbitals really looks kind of like a mushroom, and this picture does a better job than the video I just showed. The video makes it look like a teardrop, and if you use your imagination a little bit, yeah, okay, it kind of looks teardroppy, all right, but anyway, bear with that kind of analogy. Carbon has the 4 sp3 hybrid orbitals, and like the fluorine in BF3, the hydrogen here are not hybridized. They're just using their good old atomic orbitals. So hydrogen has a 1s1 orbital. It smashes into one of the sp3 orbitals. You've got that great overlap, which makes the sigma bond, and voila, that's how we get tetrahedral CH4. So when we talk to each other about hybridization, we talk about the hybridization of the central atom. The carbon is sp3 hybridized, just like the boron in BF3 was sp2 hybridized. Notice that the electron pair geometry is the key to finding out the hybridization. Every time you see tetrahedral, it's sp3. Every time you see trigonal planar, sp2, etc., etc. This is an overview of what we just looked at here for methane. The left-hand yellow box is a before, all right, kind of thing where it shows the 2s2, 2p2, and the right-hand side is what happens after hybridization. So you go from the s and the 3 2p's into these 4 equivalent energy sp3 hybrid orbitals. They're all the same energy, so the electrons will evenly distribute. You don't pair up until there's no more room. And then when you make the molecule, down here in the lower right kind of, the blue little blobs, those are the hydrogen 1s orbitals, and they're smacking into the sp3 orbitals. The overlap between them is the actual sigma bond that we draw, what we draw right there. Pretty cool. So that's a great way to think about hybridization or valence bond theory. The electron pair geometry is the key to determining the hybridization part. So if you have 4 bonds around the central atom, it's going to be sp3. If you have 3 bonds around it, it's going to be trigonal planar, and it's sp2. We haven't looked at yet, but you can probably imagine if you have something that's linear, it's going to be sp hybridized. The trigonal bipyramid is sp3d. Sometimes I refer to that as d sp3. I put the D first. That's an older way of doing things. It is the same thing. I like the D orbitals a lot, so it's hard for me to get rid of that one. But the new way is sp3d, fine. And octahedral sp3d2, and you got it. It could be d2 sp3 as well. So the first thing I want to point out here is that, yeah, electron pair geometry is the key to finding out what the hybridization is. And it's one of these 5 terms, sp, sp2, sp3, sp3d, sp3d2, that you're going to use to describe it. Now, we're going to come back here in a little bit and talk about what the heck the other orbitals are up for. We saw that in trigonal planar sp2 bf3, there was one unused p orbital, and there is a use for those. I'm going to show you here in a little bit. We'll talk about that. The Vesper guide in your companion will just give you more information on these different terms too. Here's a question. What hybrid orbital set is used by the nitrogen atom in ammonia NH3? Okay, so this is a kind of question that you might see. And what you should do on a problem like that is first draw the Lewis structure, all right? And from the Lewis structure, you can find the electron pair geometry. And from the electron pair geometry, you can find the type of hybridization to use. Now, we looked at ammonia extensively in the last chapter. Ammonia, I'll try and draw it up here when you figure it out. Nitrogen is connected to 3 hydrogens, and there's a lone pair on it. So that's a very quick and dirty Lewis structure for ammonia. Around nitrogen, you have 3 bonds to atoms and 1 lone pair. That's like 4 clouds on the geometry and polarity guide. 4 clouds with 1 lone pair means that the geometry, the electron pair geometry, is tetrahedral, and the molecular geometry, trigonal pyramid. We don't really need the trigonal pyramid here. We just need the tetrahedral part. And anytime you have something tetrahedral, like we talked about, like NH3, it's going to be sp3 hybridized. So we would say the nitrogen is sp3 hybridized in this case. Here's some more examples of how the different things come out, especially with sp at the top, sp2, and sp3. If you have something that's sp hybridized, like beryllium dichloride or beryllium chloride, depending on how you're describing them, the bonding, beryllium itself would be sp hybridized, so that means it's only using 1 s and 1 p orbital. The 2 orbitals each have 1 electron. They're going to be as far apart from each other as they can, so it takes up linear, BeCl2. And then under that, you have the BF3 and CH4 examples we talked about earlier. The punchline of hybridization, though, is the electron pair geometry will help you find the hybridization. So anytime you have a linear electron pair geometry, it will be sp. And anytime you have a tetrahedral electron pair geometry, it will be described as sp3. So here's just an example of what we can do. And I want you to kind of do this. And you can pause the video if you want before I talk about the answer. But what I'm going to do is the arrows are pointing at an atom. And I want you to go through with me and we'll figure out the hybridization of those different atoms. And again, the answers here will be sp, sp2, sp3, sp3d, or sp3d2. So the first one there, that nitrogen, the nitrogen has 1, 2, 3 bonds to other atoms, hydrogen and a carbon, and a lone pair. So 4 clouds means that the electron pair geometry is tetrahedral, and anytime you have tetrahedral, sp3 hybridized. Cool. Now let's go to the red one. That red one points at a carbon. The carbon has 4 bonds to atoms around it. 4 bonds, once again, tetrahedral. And again, anything tetrahedral, sp3. The carbon in the green box there is pointing at a carbon atom. That carbon there is connected to 3 atoms: a carbon on the left, a double bond oxygen above, and an oxygen single bond to the right. Now, remembering that double and triple bonds count as one cloud. The double bond is one cloud, the bond to the single oxygen is one cloud, and the bond to the carbon is one cloud. That's 3 clouds. So 3 clouds means trigonal planar, and anytime trigonal planar, sp2. Finally, the last one, the yellow box, points to the oxygen. The oxygen has 2 lone pairs and 2 bonds, 4 clouds total. It's our good friend tetrahedral once again. There's a lot of tetrahedral answers here. Anyway, tetrahedral once again, sp3. So hopefully you can see that this is pretty chill. If you had a linear atom, then it would be sp. If you had a trigonal bipyramid, it would be sp3d, octahedral sp3d2, etc., etc.